Next, we will be welcoming Dr. Gigi Richard. She's currently the director of the Water Center and a professor of geosciences at Colorado Mesa University in Grand Junction, Colorado. She holds a Master's of Science and a Ph.D. from Colorado State University and a Bachelor of Science from the Massachusetts Institute of Technology, all in civil engineering. She created the Watershed Science Program and co-founded the Water Center at Colorado Mesa University, and they facilitate education, research, and dialogue on issues facing the Upper Colorado River Basin. Her recent work has focused on the impacts of vegetation removal on channel morphology of the Colorado River, and today she'll be speaking to us about climate change, riparian vegetation removal, and channel change on the Colorado River.
All right, thank you very much. I'm excited to be here. This is my first time at the Restoring the West conference, and I've been really impressed with the talks. I've really enjoyed my time here, so thanks so much for the invitation to come talk to you all. I tend to move around a lot when I talk, so I'm going to try to stay here and stay focused on facing forward. That might be a challenge, though. So my talk today is going to be tying in a little research project that I've been working on, looking at how the Colorado River has been responding to the removal of Tamarisk and Russian olive in the Riparian zone, and tying that into what are some of the predictions for peak flows, because peak flows are really crucial for initiating channel change. So how will peak flows, how are they expected to change with climate change? Which there's a lot of uncertainty there, so I don't really have any answers. I have more questions than answers there. So just to orient everybody, the city of Grand Junction is located here at the confluence of the Colorado and the Gunnison rivers. It's called Grand Junction because the Colorado upstream of the confluence with the Green River formerly was called the Grand River. The state of Colorado co-opted the name of the river back in the 1920s, decided that above the confluence with the Green, it should continue to be the Colorado. So in the past, the Colorado actually started where the Green and the Colorado came together in Utah. The state of Wyoming and the state of Utah were not so happy about that, but the name is stuck, and the city of Grand Junction is so called Grand Junction. So the study site that we're looking at is right here. It expands above the confluence with the Gunnison and below. And to just give you a little orientation here, this is one of our sites following Tamarisk removal. You can see where the property boundary is right here, and further upstream there is quite a bit of Tamarisk and dense woody riparian vegetation on the bank line. I'm going to do a little shameless plug. The Water Center at CMU hosts an annual conference. It's in a couple of weeks, November 2nd and 3rd. We focus on water issues in the Upper Colorado River Basin, and your own Utah State, Jack Schmidt, is one of our keynote speakers. He's going to be talking about ecosystem management in the Grand Canyon on the Colorado River. Also, I put out in the lobby a couple of our publications. We do have a technical and scientific report series that may be of interest to you all, and we have one in press now that should be out soon about conservation planning in Utah along the Colorado River that was produced by the USGS, and we're doing the publication of it and handling the peer review process. So please help yourself. There's the agenda and the registration form are out on the counter out there if you're interested in the conference. So this little project that I've been working on related to Tamarisk removal and channel change was initiated by a phone call from the city engineer one day, who's after the 2011 floods said, "Hey, Gigi, come meet me out by the river because we've got some problems with the bike path." And we were trying to figure out what to do. So we went out there, and this is what he showed me. You can see the bike path coming along here. They've already been reconstructing it by the time Google flew over it. But you can see where the bike path was eroded away here and where it was eroded away here. So we're standing on the bank talking about why this might have happened. And let me show you a couple aerial photos, and maybe you can pick up on what might have happened. So, oops. So here's 2001. So you can see the alignment of the path, this one site where we had erosion and the other site. Here's 2007. And here's 2008. Let me go back. So what changed between 2007 and 2008? The city went in and removed all the Tamarisk along the bank line in this area. This erosion site up here, we actually don't think it had anything to do with tamarisk removal. There was a really crazy hydraulic that formed as the floodwaters were receding after the 2011 flood that created this really amazing eddy and just chewed away at the bank line there. But this section was the area where there was quite a bit of tamarisk removal, as you saw in that aerial photo, and we had some significant bank erosion. So this got me thinking, as we're moving up and down the river and removing tamarisk, which is becoming a very popular activity in riparian restoration, and I think that's a wonderful thing, and we'll talk more about why. But as we do that, maybe we need to consider what the potential destabilizing, result may be along the river. And so we got some funding from the Colorado Water Conservation Board. I've been working with the Tamarisk Coalition, and I'll talk a little more about this project. But first, let's talk about this amazing plant, tamarisk. So tamarisk was introduced into the western U.S. in the late 1800s as an ornamental and for channel stabilization, and it does that very, very well. We were already starting to see changes in the rivers in the western U.S. by the 50s, and by 1970s, Will Graff wrote this paper looking at the Green River and how the channel had been stabilized by the invasion of tamarisk. And so the combination of the regulation of our rivers with dams, the cutting off of the peak flows, and the invasion of tamarisk has shifted our rivers into a more single-thread configuration. We've lost a lot of backwater and side channel habitats, and our rivers in general are much more stable. So tamarisk is an amazing plant. It has a really deep taproot. It concentrates salts from the soils. The salts accumulate in the needles. When it drops, it's deciduous. When it drops its very needle-like leaves, it forms a salty duff layer. In a mature tamarisk stand, there's very little undergrowth, and it's really difficult to get other vegetation to regrow after you remove the tamarisk without disturbing that salty duff layer. It has a very high stem density, so it creates really high hydraulic roughness in the floodplain. So when you do have overbank flooding, that high hydraulic roughness slows the flow down and allows the sediment to deposit, and you end up with very erosion-resistant banks. So in that early study, and there have been many studies since that have confirmed this stabilization effect of tamarisk, our 27% reduction in average width on the Green River, and that was back in 1978. So the next question is, well, if we remove tamarisk, what happens to the channel? Does it respond and erode? Does the channel change? Do we have destabilization? So we'll look at 3 different studies done in the western U.S. where they looked at channel change in response to tamarisk removal. One is in along the Rio Puerco in New Mexico. There was a reach of the river that they sprayed with an herbicide. Oh, so I should mention also that tamarisk is super resilient. If you cut it, it will resprout very quickly unless you get herbicide on the stump within about 15 minutes. So cutting it doesn't work. It's very fire resilient. If you burn it, it grows back. It's very resilient to flooding, and it's pretty resilient to drought because it has this really deep taproot. So a tamarisk stand can actually extend farther away from the bank of the river than the native riparian habitat. An individual tamarisk tree doesn't necessarily transpire more than the native willows and cottonwoods, but you can have a denser, wider stand of tamarisk that in total can use a lot more water. So a lot of the interest in removing tamarisk comes from the motivation of trying to conserve water. So they sprayed this reach along the Rio Grande. There's another river where Ellen Wall at CSU did a study looking at, I lost my pointer, here we go, down in Canyon de Chelly in Arizona. And then another one in the San Rafael River in Utah, that actually this study was looking at fish habitat restoration. They actually took woody debris from the removal and in a big flood that got washed into the river, and so they were looking at aquatic habitat restoration. So what did these studies find? So in the Rio Puerco, what they found, so this shaded gray, I don't know if you guys can see that, this is the x-axis goes from upstream to downstream. And the shaded gray reach is the sprayed reach, and the downstream reach was not sprayed. And this top box is looking at fraction of bank eroded, and then here this is the cross-sectional area erosion, the average channel width increase from pre-flood to post-flood, and then cumulative sediment volume. So it's pretty clear that there was more channel change in the sprayed reach than in the control reach. And the sprayed reach actually increased by 84% in width. In Canyon de Chelly, they looked at 3 different tamarisk removal methods: cut stump, which is where they cut the stump, put herbicide on it; whole plant removal, and in this case they used backhoes to actually literally rip the entire plant out, including the root; and then a control treatment where they did no removal. And they didn't find quite as dramatic a difference, but they did find that, so if we look, this is the control, the cut stump, and the whole plant in each of these box and whisker plots, that the whole plant removal method did result in larger width changes on the order of about 12 to 14%. But they also found that neither method of removal, cut stump or whole plant, resulted in major destabilization. So the channel remained very entrenched, but they had no significant flood during their study period. And there was a pretty extensive clay layer in the bank at the toe, which is a stabilizing factor. And then they also had pretty substantial native vegetation that wasn't removed. In the San Rafael River, they looked at a treated reach and an untreated reach, and they found this is width increase, percent width increase in the treated reach versus the untreated reach. And the magnitude of widening was higher in the treated than untreated. Their study spanned the 2011 flood, which is a regional flood year for us in the West here. Interestingly, though, they didn't find within the treated area, they compared places where tamarisk were removed on the bank and at the channel edge with places where tamarisk weren't. So in a treated area, they don't usually remove every single plant. And so there were places where there were actually tamarisk left, but they didn't really see a difference there. And it wasn't actually what they expected. So it's not really that definitive or really clear that we actually see more channel change necessarily when we remove tamarisk. But one thing that does seem pretty clear is that peak flows are important, and that's something to hang on to. So the study that I did is in this 50-kilometer reach in the Grand Valley on the Colorado River. The confluence with the Gunnison is right here, so our reach spans from above the Gunnison to below the Gunnison. The orange areas are areas with greater than 10% tamarisk coverage, and these are data from the Tamarisk Coalition. Over the last about 15 years, there's been a lot of effort to remove tamarisk and Russian olive. Russian olive is another invasive riparian species that has similar characteristics to tamarisk, and it has really big, nasty thorns. So if you have to do restoration and removal of Russian olive, it's not much fun at all. And there's been a lot of activity in removal, so you can see 500 acres removed. And those removal activities have been performed by a variety of entities, including nonprofits like the Tamarisk Coalition and the Audubon Society, as well as local governments and federal agencies, state agencies as well. A lot of the Colorado state parks and wildlife areas along the river have done extensive tamarisk removal. So the purpose of our study was to measure geomorphic adjustment following vegetation removal, and we have 2 ways that we have done that. One is with field surveying, where we actually go out and measure cross-sections at 3 sites owned by Colorado Parks and Wildlife, pre-removal and post-removal. And then we've also done a GIS analysis looking at historic channel change, pre-removal and post-removal. And then part of the idea is that Colorado Water Conservation Board wanted us to come up with some standardized methods for how we would go about doing this measurement so that it could be implemented in other reaches. So first off, our field surveying efforts, I'm actually not going to spend very much time on this because our results aren't very interesting at this point. We have 1 set of pre-removal cross-sections and 1 set of post-removal cross-sections, and the river pretty much didn't change in that time period except at 2 cross-sections, which had been mobile before the removal. So not really a whole lot to report, although I think it's really interesting to have a look at what these sites actually look like. So these photos here are taken in April, following the tamarisk removal, which happened in January. This removal effort was by mastication, which is this masticator attachment that you put on a tractor, and it's at the top of the plant. It just gobbles the plant all the way down, and it spews out lots of bits and pieces of wood and debris, and it makes a big mess. And when you're hiking across these sites after the mastication, you have to be careful to not stab yourself on these spikes of wood that are left behind. Much of that debris has to be cleaned up because it's in the 100-year floodplain, and the Corps of Engineers is pretty strict about making sure that all gets cleaned up and tidied away. So here's the site in April after mastication in January, and here's that same site in August of that same year. So what we were especially surprised by in 2015, we had a really wet spring. I don't know if in Colorado everyone was calling it Miracle May. It had been really dry, and then all of a sudden it started raining and snowing in May, and it rained and snowed and rained and snowed all the way until mid-June or so. And we had a really late peak on the river. It was a really unusual runoff. But what we saw at these removal sites is revegetation came in really fast. It includes tamarisk resprouts, it includes native vegetation, and it includes a lot of secondary weeds. And so the entities that are doing these restoration efforts are starting to realize that this secondary weed control is a big part of this riparian restoration. So lots of thistles, purple loosestrife, and a number of kochia. Kochia is another really big challenge with the secondary weed invasion. And then the revegetation, of course, made our surveying a lot more challenging again as well. We were all excited here. We're like, oh, this is great. You don't have to bust your way through tamarisk thickets. But now we have thistles and all sorts of other things. So Okay, so the GIS piece. So what we did is we took historic aerial photos from some different years, and we digitized what we call the active channel. And the idea here, we're not talking the water line. This is the channel that is regularly flooded so that woody vegetation doesn't grow there. So it can be kind of challenging to actually distinguish what we actually call the active channel, and we've got some tools and techniques to try to pin that down. So for this example is one of the major erosion sites in the Grand Junction area. It was at an area where Tamarisk were removed by the Audubon Society. They did a great restoration effort, and actually beaver have moved in. There's some bank beaver that live in this area now. So, but that was the 2007 bank line. There's the 2012 bank line. So this polygon would become an erosion polygon. And so the data that I'll show you, the results, are from the measurement of these kinds of polygons. You can run a little tool in GIS that determines the distance between these two lines and creates a polygon if the lines are farther apart than a certain threshold. So the two time periods that we looked at so far are from 2002 to 7 and 07 to 12. All right, so those two time periods are distinctly different hydrologically. And as a result, turns out they are distinctly different from an erosion perspective as well. So these are the annual instantaneous peak flows at the Colorado River near the Colorado-Utah state line gauge. So that is on the Colorado River right there, so downstream from the Gunnison River. These are the peak flows at the Palisade gauge, so this represents above the Gunnison River. And you can see here's the mean annual flood. The vertical scales, the Y scales, are not the same on the two graphs. The orange line is giving us the mean annual flood for the two gauges. The light blue is the earlier time period, 2002 to 2007, and the dark blue, 2007 to 12. And you can see at both gauges, the second time period had much higher peak flows. So we had 4 peak flows above the mean annual flood. And in particular, the 2011 flood was, for example, at this gauge, which has a record from 1951. These data go through to 2013. It was the 6th highest flood on record. At this gauge, the 2011 flood was the highest flood on record because that gauge wasn't established till 1991. But so that was a pretty good flood for the channel here. So what we see as far as the response of the river is that we have a lot more erosion when we have higher flows, not surprisingly. So orange is no tamarisk removal, green is tamarisk removal. This is the early time period, this is the later higher magnitude flow time period. And we had 59 sites that eroded where there was no tamarisk removal performed, 17 sites that eroded where there was tamarisk removal performed. So the take-home message here is this river is moving whether you remove tamarisk or not, right? It is a dynamic natural river. There are places where the bank is armored with riprap or cars, concrete. But it is moving whether you remove tamarisk or not, and it needs those high flows. So in the time period, 2002 was a serious drought year. This is a much lower flow time period, a lot less erosion. So our results from looking at the size of these erosion polygons, do we get more movement when we remove tamarisk? We measured the area of the polygon and we measured the length. If we divide the area by the length, that gives us an average width, or you could think of it as area per unit length. Either way. So the lighter shaded colors are the earlier time period, the darker are the later. Orange is no tamarisk removal, green is tamarisk removal. And looking at the average width, we do see greater average width for those 17 sites where tamarisk removal occurred, and this is statistically significant. Interestingly, if we look at, this is a little bit confusing. That was kind of funny. What is that? Is that a bug? All right, this is me, not that shadowy thing. All right. So this lighter green line here is looking at sites where the tamarisk removal occurred before 2002. And the dark green line is sites where tamarisk removal occurred between 07 and 12. And what we do see is higher rates of movement when that tamarisk removal occurred a longer time in the past. So we're really excited to see, as we analyze the 2015 aerial photos, which we haven't done yet, is do we continue to see more movement as more time has passed, as maybe the root structures break down, and I don't know, we'll see. And the other interesting factor is the beetle, the tamarisk beetle, which has moved into that area, and that's not even a part of what we're looking at all yet. But okay, so maximum width of polygons, we just measured the maximum width, and again, we see that greater width, and actually our, biggest ones by far, much greater movement was at tamarisk removal sites. This difference is not statistically significant. It'll be interesting to see again when we add the 2015 photos, and again, bigger movements if the removal was earlier. Another last interesting result, these are looking at places along the channel that eroded in both time periods. So what we're trying to get at is if it eroded in 2002 to 2007, we removed tamarisks, it eroded again, is that rate of erosion greater after removal? So we're comparing, these are sites where we had no tamarisk removal here, and then sites where we did have tamarisk removal. The light color is the early time period, the dark color is the later time period. And what's interesting, and I didn't do any statistical analysis on this because we only have 3 sites here, so again, we'll see what happens when we look at 2015, but the difference here between the erosion rate in the early time period versus the erosion rate in the later time period, we do see that the post-removal erosion rate was greater at the erosion sites than the erosion rate at the non-removal sites during the high flow time period. So I can answer questions about that later if I didn't explain that well enough. Okay, so let's get into thinking about climate change. So we know that it takes high magnitude flows to produce channel change. I mean, that's not something that these studies have shown us. Geomorphologists understand this. This is something very well understood. But how high and what frequency? Well, one conventional way to get at what kind of flow do we need to get a channel to move is to look at which flows do the most work in the channel, which flows are moving the most sediment. And that's often referred to as the effective discharge. What we do is we take a flood frequency curve. So if we have discharge down here on your x-axis, and then we plot our flood frequency curve here, our higher flows occur less frequently, right? And then we take our sediment discharge rating curve, which is saying as discharge increases, the river can move more sediment. We take the product of those 2 curves, we get a curve that's our product, where that peaks, that gives us the frequency of discharge that is moving the most sediment over the long period of time. Really big floods can do a lot of work, but they don't happen very often. So it's more the moderate frequency floods, 1.5, 2 years. Some people suggest that maybe on more Dryland rivers, it may be more the 5-year, maybe even the 10-year flood, but it's the moderate frequency floods that are doing the most work, maintaining the shape and form of the channel. And it's not just a single value of flood, it's the whole hydrologic regime of that river that's really maintaining that form of channel. But for our purposes today, we're going to look at these peak floods. So the next question is, what do we know about the impact of climate change on these high magnitude flows? And from talking to my colleagues who are, working in climate science and the research that I've done, the answer is not a whole lot, and there's a lot of different stories about that. We hear, well, what we do know, let's start here. What we do know is that it's warming. So Colorado, statewide, annually average temperature, this is measured as annual departure relative to the 71 to 2000 time period. We can see these dashed lines are showing the trends over those time periods, and the trends are all going up. And the black line in the background is the 10-year moving average. So we know it's warming. What does that mean for peak flows? Well, let's think about what goes on hydrologically in western Colorado. So this, if we imagine this is our little Colorado River, Upper Colorado River watershed in Colorado, which 85% of the basin, of the whole Colorado River Basin, gets less than 20 inches of rain a year. It's only 15% of the land area in the Colorado River Basin that's producing most of the runoff in the Colorado River. Most of that land area is in the high elevations in the state of Colorado, some in Utah, and some in Wyoming. So really, when we're talking about the water generator for the Colorado River, we're talking western Colorado. So our evapotranspiration rates in the Colorado River Basin are very high. About 75% of the precipitation evaporates, only about 25% runs off. So our high ET makes the Colorado River Basin very sensitive to warming. If we add in warming, what happens? Well, we still don't really know with precipitation. We've heard that repeatedly over the last 2 days. There's a lot of uncertainty in precipitation, but we know ET rates go up and we know runoff is going to go down. So that's one of the things we do know. And we know in total that, we heard that from Jonathan this morning, that, in general, we're looking at lower runoff in the Colorado River Basin. In addition, warming temperatures lead to less snow, that decline in runoff, more precip as rain than snow, which leads to less efficient production of runoff. There's more loss to evaporation. There are more losses when we get precipitation as rain than as snow. We get more sublimation loss from snowpack. With warmer temperatures, we're going to have earlier snowmelt initiation, which typically leads to slower melt and less efficient runoff. And then there's all those confounding factors like effects of dust on snow. Soil that's exposed to the earlier meltout loses more moisture to evaporation. And vegetation have a longer growing season. We've heard this story over and over again. We have more moisture loss that includes crops as well as native vegetation to transpiration. So what does this mean for peak flows? Well, two things here. This less efficient runoff, both of those suggest that in that snowmelt runoff, we may see reduced peak flows if that runoff is less efficient. It depends on the timing of the melt. I understand it could actually, if it melts really quickly, you could actually get higher peaks, but if you have less snow overall, I don't know. And then if you get rain on snow, that's another often flood-producing event. So what we see, if you looked to the National Climate Assessment, in the southwestern U.S., we see trends, I don't know what's wrong with this, there we go, trends of diminishing flood magnitude, but also in the National Climate Assessment, we see observed increasing trends in heavy precipitation, and we see headlines like this, how climate change helped cause massive floods in Louisiana. So the other part we know is that warmer air can hold more water vapor. So these are precipitable water vapor above Denver. So for different months, giving the minimum and the max, this was the precipitable water vapor in the atmosphere in Denver in September, on September 11, 2013, which led to this. So there's definitely potential with climate change to produce higher peak flows. But maybe lower snow melt runoff floods, which on the Colorado, that may be the kind of flood that's creating the shape and form of the channel. So maybe it depends on the hydrologic regime of your system and the size of your watershed. as well. So just to kind of emphasize this snowmelt piece on the Colorado River, this is work done by Steve Fasanacht at CSU. So we've got the water year on the bottom, and of course the water year starts in October. And the top graph up here is the Upper Basin, and the bottom graph is the Lower Colorado River Basin. And the Y scale is the annual peak flow. And so these are all the different gauges in the Upper Basin, and what this is showing us is that that peak flow happens in late May and early June. That's the timing of the snowmelt. And the peak flows in a lot of these other rivers is not associated with snowmelt. So on the Colorado River and the Grand Mesa and the Grand Valley, our annual hydrograph is response to snowmelt. So we have our snowpack building through the winter, starting to melt, and then our response is the peak flow in the river. And it's this region in here that's really of interest as far as the generation of that peak flow. And so another little study I've been working on with CSU actually is looking at how does our stream flow generate from the lower elevation snowpacks. Just last year we actually saw a really interesting shift as we had good snowpack and then it started to warm up. And all of a sudden the Colorado Basin River Forecast Center was saying, oh, our flows, the predicted flows are much lower because we lost that low elevation snowpack. So there's a lot that we can learn about what happens during this time period with our low elevation snowpack. So just last couple things real quickly, looking at, whoa, come back. Okay, our peak flows on the Colorado River near the Utah state line, so this is that gauge just downstream from Grand Junction. Our mean annual flood, if we look at the whole record, almost 27,000 CFS, and okay, I'm doing something a little crazy here, but in that temperature slide, it was 1985 when the temperatures really started to take off. Also, this gives us a nice handy 30-year period, which National Weather Service and NOAA, they love to average over 30-year periods, right? So here's our last 30-year period, and we can see a decline in our mean annual flood at this one gauge, which just really got me intrigued. I'm going to get some students working on maybe looking at some other gauges to see how our floods are changing in Colorado. If we look at our flood frequency curve, so here's our frequency, our return period here, our annual peak stream flow, this is that same gauge, the whole record. If we break it at that same time period, before 1985 and after, this is the earlier part, and this is the later part, and we look at that 2011 flood, what we see is if in the earlier time period, it would have been more like a 7-year frequency, whereas now it would be more like an 11-year frequency flood. So that same magnitude flood. So this is the kind of thing that's got me thinking, like, are we going to start seeing shifts in our flood frequency curves, which can really make a difference in how our channels respond. So to wrap it up, channel change depends on high magnitude flows. We do see larger erosion where Tamarisk and Russian olive had been removed. And climate change impacts on peak flows are uncertain, and I think it'll be really interesting to see as more work comes out in those areas. And thanks to all of my collaborators on this research, and I don't think I have time for questions. Oops. Thank you.